So I've done a few practice runs with this new version of the presentation, and everyone I asked about it who watched one of those practice runs said that this one was much easier to understand than the first version, which is really good. Hopefully, if you watched the first video and did not understand what I was talking about, you will understand what I am talking about in this video. You will need to know what a floating point number is, specifically an IEEE 754 floating point number, which is pretty much everything these days, and what a 2's complement number is. A comparator is just something that takes in two bit strings which hold a number of a certain format, either in this case 2's complement and a floating point number, and says, okay, this one's bigger, this one's less than, and if they're equal, right? So if you want to have an sorry. So if you have an if statement where you say if A is less than B, the compiler will use the comparator inside the CPU to run that instruction, and we'll see if A is less than B, or if B is greater than A, or if they're equal, and so on. Okay, so for this video, I'm going to make up a fake floating point standard. 8 bits is much easier to see on screen than a 32-bit single precision, or even a 16-bit half precision. So I'll be using that. I've apportioned the bits for this quote-unquote standard as so. You have your sign bit, which is just the leftmost bit always, and I have 2 exponent bits and 5 mantissa bits. And again, if you don't know what an IEEE 754 float is, don't watch this video. Go learn what that is before you watch this video. I will not be explaining it because this video will be like an hour long, and I do not want that. Okay, and you have an exponent offset, and in this case, the standard, quote-unquote standard, says that you subtract 1 from the unsigned number in these exponent bits. So the unsigned number is 2, 10 is 2, so you subtract 1, you get 2 to the 1, and then you just sort of shift the decimal place right. And you don't have to store this 1 anywhere. You just have to store the 5 mantissa bits, because it's all for you can't have a 0 before the decimal place in a scientific notation number. It has to be a 1 in binary. For decimal, you do have to store it because it could be a 1 through a 9, but in binary it's just 1 through 1, so you don't have to store it, which is really cool. Saves an extra bit, gives you a little more precision. All right. 2's complement refresher, you have this sign bit, but that's not really a sign bit, so you have to, if you want a smaller negative number, you have to add stuff back to make it more positive, as opposed to like sign magnitude, where like -0 would be 1 with all zeros. Okay, so the reason why you can compare two floating point numbers on the same hardware as 2's complement numbers is that the two number formats have the same sort of hierarchy. And this section is going to be a little bit kind of like high level, and you might not understand that, but I have examples to follow this, and you should be able to understand it once you get there. Okay, so there's 2 sections to both of these numbers. There's the leftmost bit, which is the sign bit, and again, this isn't really a sign bit, but if you flip this bit from a 0 to a 1, it'll make the number more negative, right? If you have a positive something, and then you change it to a negative something, right, that's going to just make the number negative. Right, and then a bit flip from a 0 to a 1 in the rest of the positions makes it more positive for both the numbers. Right, and I actually have the representation here. If you flip this from a 0 to a 1, you'd add 32. And this one's a little more complicated, but we'll get to that. And similarly, if you have a bit flip in a more rightward position, it has less impact on the number. Right, so if you, for the 2's complement number, flip this one from a 0 to a 1, it'll add 32, but if you go 1 position rightward, it'll add a 16 instead. And here, if you flip this one from a 0 to a 1, it'll have less impact than if you flip this one to a 0 to a 1. In fact, this bit has 1/8 the impact as this bit flip does. Okay, so now to the examples, so you can understand a little bit better. It's probably not very concrete in your head. I know what I'm talking about, but it's hard to get until you get it. And hopefully these examples will explain it. Okay, so imagine you're the comparator, right? And you're given a number and you're told to just say, okay, tell me which one's less than the other, right? And you can look at this first bit and you notice that the sign bit is 1 on this one and the sign bit is 0 on this other one, right? That means that this will always be less than this number, right? Because the negative number is always smaller, not bigger, than a positive number. And it's the same thing for a 2's complement number. If these were both 2's complement numbers, right? A negative 2's complement number would be smaller than a positive 2's complement number. Now the exponent is where it gets a little tricky, and this is the primary reason behind the offset. right? Because of what I said back here, where a 1 in these positions makes the number more positive, you want your smallest exponent in the 2's complement number to be as little as possible. You want it to be all zeros if you can do that. And that's what the offset does, right? So this fake standard says that you have to subtract 1 from the unsigned binary in here. In this case, it's just all zeros. So 2 to the negative 1 is the smallest exponent. And if you flip it all to ones, right, you would have unsigned exponent 3 here, and then you would subtract 1 to get 2, right? And the reason why this is true, where direction makes less impact, there's nothing on the mantissa that you can do which would make this number less than this number, right? So as a sort of like edge case, you can think of two decimal scientific notation numbers. One's like 9.9 times 10 to the 0, or just 9.9, and and then the other is 1.0 times 10 to the 1, which is 10, right? 10 is greater than 9.9. So despite the second number, 1.0 times 10 to the 1, having smaller numbers and it's like mantissa, it's bigger because the exponent was bigger. And then mantissa is kind of just a gimme, right? So if you have the same sign in the exponent, you have to look at what's in the mantissa and see which one's bigger, right? So 1.00 something is smaller than 1.10 something. Okay, hopefully that makes more sense.